Hello students, this is Mr. Yao. Today we are going to talk about the second to last lesson in this unit, where we will combine vectors and matrices together to perform some transformations. First, let's review what kind of transformation we have learned. We have learned about translation, dilation, stretch, rotation, and reflection. And in this lesson, we are going to work with dilation, rotation, and reflection. Something else, at the beginning of this unit, when we were first introduced to vectors, we have seen some very familiar words from the matrices unit. So, for example, scalar. Scalar is just a plain number, and we have been performing scalar multiplication with matrices and vectors. And the answer of any kind of operation, adding, subtracting, scalar multiplication for vectors and matrices, we have been calling them resultant. And next, we have the kind of absolute value looking notation for matrix. That is to calculate the determinant. And for vector, that is to calculate the magnitude. So these are some pretty obvious similarities. But vectors and matrices are actually even closer than we thought. They have so many things in common, and in fact, vectors we have been using are matrices. They are matrices with just one row. So technically, it could be a row or a column. When we get to the example, I'll explain why I chose to just represent it as a row. It's actually for consistency in this lesson and in the next lesson. Because if we think it as, we can write it as a row or column, then there are two different setups. And if we just try to keep it always as a row, then it's very consistent to set it up. In this section, we're going to learn how thinking of vectors as matrices can help us better understand dilation, which is stretching and shrinking, rotation, and reflection. So let's first talk about how we multiply a matrix and a vector. Step 1, we are going to rewrite the vector as a matrix. Step 2, perform the matrix multiplication. And step 3, well, since we started with the vector, we got to write that back as a vector, a component vector. So here's the example. Even though it is A times V, it is technically a vector V times A. Here's the reason. Well, let's write our vector as a matrix first, a row matrix. The dimension for A is 2 by 2. The dimension of vector V is a 1 by 2. So if we actually do A times V, A in the front, V on the back, we can't because the middle numbers are not the same. So we gotta actually flip it. So we always put the vectors in the front. And that is why I'm saying we can always be consistent and keep it as a row. And all we need to do is make sure to always have the vector in the front when we multiply. So we would have a 5, 6. Multiply with a 1, 2, 3, 4. And here's the reason why I said you could also write it as a column. If you write it as a column, then that would be a 2 by 1. Then of course, in this case, you can multiply. But in this case, as a column, you gotta put the vector on the back. So you see, they are set up slightly differently. That's why let's just be consistent, rewrite it as a row, and put it in the front. Now, time to do some matrix multiplication. Let's draw the lines because our result, that's a 1 by 2, that's a 2 by 2. We are going to end up with a 1 by 2. So 5, 6, 5, 6. And then we have the 1, 2, 3, 4. 1, 3, 2, 4. Make sure you multiply the pairs and then add. Multiply the pairs and then add. You are basically counting by pairs, and every single pair is going to be multiplication in between. Then with all the pairs, we're going to add them together. Eventually, you are going to get 23, 34. But of course, we are going to rewrite it as a vector using the pointy brackets, 23, 34. And that is how we do multiplication with matrix and vector. Now moving on, the first one, dilation. To dilate a vector V is a V multiplied by the scale factor matrix. This is the scale factor matrix. The C would be the scale factor. So for example, we have the vector 1, 2, so 1, 2. And the scale factor is a 2, so that means we have a matrix of 2, 0, 0, 2. So let's do our multiplication. Oh, actually, let me graph the first one. So that is my typical 1, 2, the original one. Then I have 1, 2, 1, 2. And I am going to have 2, 0, and 0, 2. And now let's put in the multiplication and addition. And this is where you kind of could see why it has to be this kind of matrix setup. Because the 1 represents the horizontal component, basically the x, and the 2 represents basically the y. So when we want to dilate the 1, we got to make sure it's 1 multiplied by this first number, but the other number has to be the 0, so the y is not being added to the x. That's why the first column is going to be 2, 0, because this position is going to be affecting that x. And this position is going to be affecting that y in the second position. That is why it's going to be 0, 2. And then we are going to get a 2, 4, which we can write it as a vector, pointy bracket, 2, 4. So let's draw it. And there we go. It is actually going to be on the exact same line, overlapping each other. And that's how it's supposed to be. It's dilation. So we're not changing the direction. We are just changing the magnitude. We are enlarging it in this case. And we're going to use a v sub 1 to represent the new vector. Next, same idea. We have 1, 2 to begin with. And the new matrix, the scalar factor matrix, the scale factor matrix is going to be half, 0, and 0, 1 half. So we are going to multiply 1, 2, 1, 2. And in this case, we are going to put on 1 half, 0, 0, 1 half. So we are going to get a 1 and a 1, actually a 1 half and a 1, vector 1 half, comma 1. The arranged vector is right here. And the new vector is going to be halfway, so right here. That is my v sub 1. The other one is my vector v. Okay, again, as you may notice, we have this column as zeros, this diagonal as zeros, because they shouldn't be affecting our horizontal component or vertical component. These two are the ones that should be affecting. So now let's move on to rotation. Rotation. To rotate a vector, multiply it by the matrix. These are some general matrices, but these are the very special ones for each of the transformations. To rotate 180 degrees. If you think about it, rotate 180 degrees means if you are pointing this way, let's say if you are pointing this way, it's going to be flipped completely to the other direction. And that is still in forming a straight line. And that is why it's still that same diagonal compared to the dilation that has the number, and the other diagonal being the zeros. As for why they are -1, because we're not changing the magnitude when we do a 180 degree rotation. The magnitude stays the same, but the direction is completely opposite. That's why the horizontal component needs to be the opposite, -1, and the vertical component also needs to be a -1, the opposite. For clockwise and counterclockwise 90 degrees, as you can see, this time they are different. It's the left diagonal, there are zeros, and the other diagonal are ones and -1s. So now let's have a look at some examples. First one, right here. 1, 2, multiply with 0, -1, 1, 0. These questions are asking you to perform the transformation, draw the resultant, and describe the transformation. So let's go ahead and calculate out our new vector. So we have 1, 2, 1, 2, and then we are going to have 0, 1, and -1, 0. Multiply, add. Multiply, add. We are going to end up having I'm just going to change it into a vector already, a 2, -1. So we started with 1, 2. That's our vector v. But we ended up getting a 2, -1. That is our v1. And you can clearly see that is rotating 90 degrees clockwise around the origin. Okay. Good news is, for all the rotation we're going to be working with vectors and matrices, they are going to be rotating around the origin. Now, again, just like I was mentioning before, because we are kind of changing the x and the y, so in this case, the 0 is going to be in their not quite usual position. The zeros are actually on the left diagonal, and the ones and -1s are on the other diagonal. For question B, same thing, 1, 2 times negative 2, 0, 0, negative 2. And we are going to end up getting a, let me do the multiplication, 1, 2, 1, 2. That is going to give me negative 2, 0 here, multiply, add, and 0, negative 2, multiply, add. So we are going to get a negative 2, comma, negative 4. So let's draw it out. First, that is my original matrix. My new matrix is going to be negative 2, negative 4 right here. And as you may notice, it's not, for sure it is rotating because it's pointing to the other completely opposite direction. So rotate 90 degree, well, not 90 degree, actually 180 degrees around the origin. And that's not the only thing, because you can see the size changed. That is going to be dilation by 2 around the origin. That's that's question B. Moving on, 1, 2, then we have negative 2, 0, 0, 2. So let's do our multiplication. 1, 2, 1, 2, and we will have negative 2, 0, multiply, add, and 0, 2, multiply, add, which gives us a negative 2, comma, 4. So let's graph them. First, we have 1, 2, that is my vector. Oh, give me a sec. Okay, I have my vector. That's a lot of extra drawing that I don't need. There we go. And then we have our negative 2, 4, which actually is here. And if you look at it, that is clearly not 90 degree. A 90 degree would actually be pointing like around this direction. So that is clearly not a 90 degree. But the matrix looks so similar. In this case, it is actually reflection. The reason I still put it under rotation is because we are going to talk about reflection next. But at the same time, I kind of want you guys to make a comparison. If you compare B and C, you may notice these two numbers are the same and then the other diagonal are zeros. So when these two numbers are the same, it would have to be either dilation or 180 degree rotation. Dilation would be two positive numbers that being the same. So you are just kind of enlarging it or shrinking it. If you have two numbers that are the same and they're negative, that would be rotating 180 degree because now it's pointing to the other completely opposite direction. But for C, yes, you still have the same diagonal being zeros. The other two numbers, they are not the same. And this is where it could be reflection. Because if one of them is going to the opposite direction, that means you are not just kind of changing one quadrant over. So, for example, from the first quadrant going to the second quadrant, that is just reflecting over the y-axis. So even though they are similar, they are actually different. You do need to actually be able to tell them apart about which transformation it is and which matrix to use for specific transformation. So lastly, let's talk about reflection. To reflect across the x-axis about the origin, use the matrix 1, 0, 0, negative 1. If you are reflecting over the x-axis, that means something on the top is being reflected over to the bottom. Basically, the y-coordinate would change. That is why the negative 1 is inside the second column, because that is going to change the y-coordinate. And for the other one, if you are reflecting over the y-axis, that means it's like from the left side to the right side. That means the x-coordinates are changing. That is why the negative 1 is in the first column to change the x. So example 3, reflect across x-axis, 1, 2, we're going to multiply by the correct matrix. Reflect over x-axis, so y is changing. That means it's 0, negative 1, and 1, 0 right here. So we are going to perform our multiplication. 1, 2, 1, 2. And then we are going to get 1, 0, multiply, add, and 0, negative 1, multiply, add, which gives us a 1, comma, negative 2. So here it is. My original one is right here, my B. My new one is 1, -2, so it's pointing down right here, B1. And that is clearly reflecting over the x-axis. Here's the thing, let's say you got this matrix wrong, then your graph would show you that you didn't perform the right transformation. So next, it's time to look at the very last one. We are going to reflect over the y-axis. So 1, 2. Since it's y-axis, but the x is changing, so that is going to be -1, 0, and 0, 1. Multiply, we have 1, 2, 1, 2. Then for the columns, we have -1, 0, multiply, add. We have 0, 1, multiply, add. And that is going to give me -1 and 2. So let's graph it. For the first one, we have 1, 2, which is our original v. And for our new one, it will be -1, 2 right here. They're reflecting across the y-axis. And that is everything for this lesson. Thank you.